Welcome to the quick session 3 applications of Laplace transform. The Laplace transform is used to evaluate infinite integral and solve ordinary differential equations. First of all, we will see the various steps involved in evaluation of infinite integrals using Laplace transform. Step 1 is express given integral in the form of Laplace transform by choosing a suitable value for e raised to minus as. Second step, evaluate the Laplace transform, and third step, give back value to s to get exact value of integral. Let us see an example. Evaluate integral 0 to infinity sin 4t dt. When we rewrite this integral using an e raised to function e raised to minus 4t within the integral and put s equal to 0. When we put s equal to 0, we will get back the original integral. This is nothing but Laplace transform sin 4t. Evaluate Laplace transform sin 4t as 4 by s square plus 16. Put s equal to 0 here. So 4 by 16 and final answer is 1 by 4. The second application is solution of ODE. The three important steps involving ODE solution is 1. Apply Laplace transform on both sides of the given ODE and substitute initial values. Step 2. Solve for y bar of s, and step 3. Apply L inverse on both sides to get the solution. For example, consider this problem. Y double dash plus 16y is equal to 4 under delta of t minus 3 pi with y of 0 equal to 2 and y dash of 0 equal to 0. To solve this first step, we apply Laplace transform on both sides. That is, L of y double dash plus 16y is equal to 4 into Laplace transform Dirac delta function with the threshold 3 pi. Then L of y double dash is s square into y bar of s minus s into y of 0 minus y dash of 0 plus 16 into L of y is y bar of s is equal to 4 into Laplace transform delta of t minus a is e raised to minus as. So here e raised to minus 3 pi s. Then we substitute the initial values y of 0 is equal to 2 here and y dash of 0 equal to 0 here. We got s square into y bar of s minus 2s plus 16 y bar of s equal to 4 into e raised to minus 3 pi s. Clubbing terms of y bar of s together, we get s square plus 16 into y bar of s minus 2s equal to 4 into e raised to minus 3 pi s. Now we solve for y bar of s, that is y bar of s equal to 4 into e raised to minus 3 pi s by s square plus 16 plus 2s divided by s square plus 16. The next stage is the last stage. We apply L inverse on both sides. L inverse of y bar of s gives y of t. Here e raised to minus 3 pi s in the numerator. So if there is a unit step function u of t minus 3 pi here. So you take L inverse of the remaining portion, that is 4 by s square minus 16, then into u of t minus 3 pi. L inverse of 2s by s square plus 16. So y of t is equal to L inverse of 4 by s square plus 16 with the t tends to t minus 3 pi with u of t minus 3 pi plus 2 into L inverse of s by s square plus 16. This is sin 4t. Now we have to replace t by t minus 3 pi into u of t minus 3 pi plus 2 cos 4t. Then when we replace t by t minus 3 pi, I got sin 4 into t minus 3 pi into u of t minus 3 pi plus 2 cos 4t. But unit step function takes only two values 0 and 1. We make use of that. When t minus 3 pi is negative, this u of t minus 3 pi is 0. When t minus 3 pi is negative and 0 less than t less than 3 pi. So in that case this becomes 0. So the first term cancels. So 2 cos 4t. When t greater than or equal to 3 pi, t minus 3 pi is positive. In that case unit step function gives the value 1. So sin 4 into t minus 3 pi plus 2 cos 4t. But sin 4 into t minus 3 pi is sin of 4t minus 12 pi. Sin of 4t minus 12 pi. 12 pi is same as 0. That is sin 4t. So sin 4t plus 2 cos 4t. In this way we can solve ordinary differential equation using Laplace transform. So be safe and be productive. Wish you a happy Easter. Thank you very much.